In this video, I'm going to be talking to you about sampling, sampling distributions, central limit theorem, and also hinting towards a p-value. And I'm going to be drawing on data from the population of the 1,000 largest cities in the world as of 2008, and I'm going to be using dynamic statistical software. So here I have a histogram showing the distribution of the populations of the 1,000 largest cities in the world. And I want you to think for a moment about the center, the spread, and the shape of this graph, and think about how you would describe those three things. And maybe pause the video for a moment while you think about that. Now that you've had a minute to think, one of the first things that's obvious to notice is the shape of this graph, which is highly skewed to the right. And with the farthest bar being out here at around somewhere between 10 and 11 million, there's 5 cities in that bar. And that may be an outlier here, but there's all these other bars here leading up to that where it's still obviously skewed even without some of the outliers or things we might consider to be outliers compared to the rest of the cities. And thinking about center, I hope that one of the things that you noticed is that with 1,000 cities, the median will be city number 500 or between 500 and 501, the population halfway between those two. So it'll be in this bar somewhere because there's more than 500 cities in this tallest bar. So the median is in this bar somewhere, and we don't know exactly what the population is, but somewhere between somewhere less than 1 million. And then the mean could be in that bar somewhere, but hopefully you remember that a skewed right distribution pulls the mean in the direction of the skew because those values are increasing the sum away from what would be a symmetric distribution. And so that will possibly be in this bar. It could be in this bar. We'd have to calculate it to be sure. But the mean is going to be pulled to the right of that. And also there's quite a bit of spread, ranging from somewhere less than 1 million all the way up to 11 million. That's quite a bit of spread when you're talking about population. And so high amount of spread or variability, skewed right distribution impacting the centers with the mean being larger than the median. And now I want you to consider a possible situation where you are tasked with estimating the distribution of the 1,000 largest cities in the world, and you're working on data from 2007 to do this. Let's say. So, let's say you're going to do this, and you're thinking, okay, this is going to be expensive. I have to go to some of these cities and somehow pay for a census of these cities in order to get an accurate representation of population in those cities. And so maybe you think, well, I'll just start with 5. I'm just going to select 5 of the 1,000 largest from the 1,000 largest cities in 2007 to estimate what it might look like in 2008. And so you might be thinking to yourself, are you crazy? That doesn't sound like it's going to work. 5 of the 1,000 largest cities? Just bear with me. There is a pedagogical point to this to think through. So here in this image, the data is actually in the top left quadrant. In the top right, you see the dot plot of the actual distribution. So this is the actual 1,000 largest cities in 2008. So you can see it goes up there. And then in the bottom left here, we have the first sample of 5. So I've randomly selected 5 cities from the list, and you can see them here. So the first city was 394,000, 639,000, 405,000, 832,000. So nothing too outrageous here. They're pretty close together, and they're basically in that first bar of the histogram, all 5 of them came from there. That doesn't mean all of them are going to do that if I do this again, but and then on the right side here, this is the mean of those 5 cities. So it's obviously less than a million. Here's a million, so the first bar would be somewhere in here, right? And then so it's important to think about that, and we're going to now randomly sample from this 1,000 largest cities and watch what happens to the distribution on the right. So as I refresh this to grab a new one, so see here, now we're up around 2 million. And you can see this distribution looks different. So now we have a little bit more spread here with these 5. And as I continue to do this, you'll notice some of the random samples of 5 are close together and some are spread apart like this one. And the means of each of those samples of 5 on the right in the green dots, those are also becoming more spread out as that happens. So if I continue to do this, I want you to think about what's happening to the distribution and what it looks like. So, as you've been thinking, watching what's happening, I want you to consider for a moment whether or not you think that this is an accurate way to represent the 1,000 largest cities in the world. And at this point, there could be 2 different thoughts running through your head. So I'm going to pick at one of them first. The first one is you might be looking at this distribution in green, which is all of the means of each of the samples of 5. So this is what we call a sampling distribution, and we've actually created it. It's not theoretical, it's real, right? We've sampled groups of 5 over and over and over and over and over again and took the mean of those and put them over here. That's what a sampling distribution is. So consider that this is all the possible things that could happen if you took one sample of 5. So if you were going to do this in reality, you wouldn't be taking this many samples of 5. You would just have one of these green dots in the situation that I posed to you. And so one thing you might be thinking is, well, it looks like sort of like the distribution of the actual 1,000 largest cities in the world. So maybe this is a good thing to do. Another thing that you might not realize, though, is that you only get one of these. So let's say you do a sample of 5 and you get this green dot here, which is somewhere around 500,000, we'll say. Okay, so let's say you do that, and then you might be close to the average of the 5 largest cities in the world, of the 1,000 largest cities in the world, excuse me. So your sample of 5 might accurately represent the average or the mean of the 1,000 largest cities in the world. Or maybe you get this dot over here, and you say, oh, well, the center must be somewhere close to 3 million. Well, that's not true. We can see that up here, right? That there's no way it's going to be that large. And look at the range here. We've got everything from close to 0 all the way up to 3 million or so. And so we're not getting a very good, accurate way of doing this. So imagine that you are playing darts and you get darts that you're trying to hit the center, but some of them are really spread out and they're all over the whole dartboard. So you're not very accurate at being able to say, I'm going to hit in a particular place. That's similar to this. So we're by sampling a group of 5 over and over again, we get a huge amount of variability in the possibilities that we're trying to target the mean of the population. So we have extremely wide range of possibilities around that. So let's say if we picked, if we had this green dot here that was, say, at 1 million, you might have to say, well, because I'm only taking a sample of 5, I know the margin of error is really, really wide. So let's say the mean population of the 1,000 largest cities in the world is a million, give or take a couple million. We don't want to have to say that. Your boss might be like, hey, try again, please. That is not helpful. So then you go back to the drawing board and you think, okay, well, what can I do next? I maybe need to increase the number of cities. So I've got to spend some more money. So let's say you say, okay, well, that's okay. I'll pick 20 of the 1,000 cities. So let's try it again with 20. So as you can see, if you're looking at the sample on the left, we sort of hope that this sample on the left looks somewhat similar to the sample in the top right, because the closer it represents the actual distribution, the more likely our mean is going to be more accurate. So if we keep on doing this, I want you to think about what's happening here and what these samples look like and whether or not we're getting closer to what we want. So, dot plot looks different than the previous one. It's shifted a little bit to the right, so we don't have as many things down here. We don't have as many extremes on the upper side. And it's not quite as skewed. So if we compare it back here again, this one is a lot more skewed. Things are clustered more towards the left and more spread out tail on the right. And with the samples of 20, the means of those samples, the sampling distribution, is not quite as heavily skewed. The tail is shorter, and things are more not quite as clustered on the left. They're shifted a little bit further in, rather than being right up against the left. And so when we think about this in terms of accuracy, if we only get one shot at this and we get one green dot, have we improved the chances of getting closer to the actual mean population of the 1,000 largest cities in the world? You might say, well, no, it still is really spread out. Like, you still have everything from 200 or from about 500,000 all the way up to 2 million, 2.5 million, we'll say. And so there's still a big range of possibilities in there, and it's unclear which dot we might get, because we could get this dot way out here, but of course it's more likely we're going to get one of the dots in this section here where there's a higher density, but it could happen that we get this one out here and then we're really far off from the mean. And so it's better, but it's still not good, right? We still have quite a bit of range, and it would be nice if this was a little bit better. So then you go back to the drawing board again and say, well, what if we then do 10% of the city? So let's see what happens when we do 100. And you can already see that the distribution on the bottom left looks more similar to the distribution in the top right, the actual distribution. And if we take samples of 100, we're going to see this look a little bit different. So I'm going to give you a minute to think about this. So one of the things that I hope you noticed is that on the left side, you might have noticed that the distribution of each sample of 100 did look pretty similar to the actual distribution. It pretty much stayed that way. Sometimes the tail was shorter, sometimes it was longer, but it mostly stayed like that. And then on the right side, look at what has happened now. It's almost as if the distribution is pointing us toward the mean. It's highly symmetric. The distribution is much narrower in range, so there is less of a possibility of getting extreme values that are far away from the actual mean of the 1,000 largest cities. So we can see here the middle here, so we might be estimating that the actual mean of the 1,000 largest cities in the world is somewhere around, we'll say like somewhere around 1.2 million. And then we see that we could get values all the way from a little bit less than a million, we'll say 750,000, all the way up to we say 1.75 million. So from 0.75 to 1.75 million, it's a much smaller range, and it gets us closer, and we're more likely to get one of these samples in the middle because there's a lot more density here. So it's more likely we'll get something closer to the mean, less likely we'll get something extreme on the ends, and it is symmetric. So the mean and the median are going to be very close to one another, if not basically identical to each other. And so this is a lot better, and we get more accuracy. So this is like throwing darts and getting all your darts really close to the target that you're trying to hit. So if the target is the middle of the dartboard, you're getting things that are very, very close to that center. Sometimes, and more often than not, things are hitting in the middle. And this is the central limit theorem. The central limit theorem doesn't have to do with data itself, but with the sampling distribution, that if you randomly sample from a population, regardless of whether it is highly skewed or symmetric, as the sample size increases that you're randomly sampling, your distribution will become more and more like a normally distributed distribution, which means it's going to be symmetric. And so with smaller sample sizes like we saw here, you're not going to see that shape come out, and that's going to lead to a big range of error in your estimating of the population mean, we'll say. So central limit theorem says this, that as the sample size increases, your distribution, your sampling distribution shape will become more and more symmetric and will conform to a normal distribution. And so one of the things we can look at here, you can see that the actual population, the mean is 1.15 million, and the standard deviation is 1.5 million. For our sample of 100, our sampling distribution of 100, the mean of those samples of 100 is almost identical to the mean of the population. And of course, I stopped at 291. So 1.14 million, the standard deviation is 142,000. So the standard deviation of the sampling distribution is pretty small, only differing by this isn't the range, this is the standard deviation, right? But the standard deviation is pretty small. And so that means that about 2/3 of the data is going to be within a range of about 300,000. And we can see that here, 1 million on the left side, 1.2 million, close to 1.3 million on the right side. So, and of course, 1.14 million is right smack dab in the center of that. So within one standard deviation, we get a really close, tight look at what the possibilities are. So the margin of error is small, although there's always a margin of error, right, when you're estimating something from a sample. All right, now to go on to another idea. So what I have done is I've taken our sampling distribution and I've created z-scores from them. And in case you need a refresher on what a z-score is the taking each of the points and basically figuring out how many standard deviations away each point is from the mean. So for instance, this data point is 0.71 standard deviations above the mean. And the formula is really simple. You take the actual mean, subtract the actual data point, and subtract the mean of the distribution of the entire sampling distribution in this case, and divide by the standard deviation. And so what that does is it produces this. On the top is the actual sampling distribution. So this was the samples of size 100, and on the bottom is the z-scores of those sampling distribution. And notice that the shape is identical. They're both symmetric. It does not change what it looks like. It just changes the scale. So for instance, this data point here, which you see it highlighted it up here, is still at a little above 0.5. So we'll say like maybe around 0.6. And so it's at the same spot, and that data point is somewhere around 125,000, or sorry, 1.25 million. So that data point of 1.25 million is about 0.7 or 0.6 standard deviations above the mean. And the mean is here at 0. So because the mean is 0 standard deviations away from the mean. So the mean is here at 0, and we remember the mean is at about 1.14 million, so that's here. Now, something I want you to think about is what happens if we get a data point out here. Let's say this one. This data point is really far away from the mean. And if we get that data point way out here at around 1.6 million, we won't know that that data point is really far away from what we should be doing, and that it's sort of an extreme value in the sampling distribution. However, if we know what the sampling distribution should look like from a theoretical perspective, we could estimate whether it's far away or not. So let's say that we get this data point, and we want to know, well, is this an extreme event? Or, for instance, if this was the distribution of all of the sampling distribution, we might be saying, has the average population of the 1,000 largest cities now changed from 2007? So let's say this is 2007 data, and we do this and we get this value for 2008 data. Is it far enough away that we would tell people, hey, the population has increased substantially. It's significantly different than it was last year. So what we can do if we know the sampling distribution is just calculate what the likelihood is of getting this value that's really far away. So one thing that is helpful here is to think about the fact that we have a p-value, or I mean a p-value, we have a z-score of somewhere around, let's say, 3.3. And so this z-score that's way out here, that's pretty far away from the mean. And if you remember things from thinking about normal distributions, things that are outside, that are beyond 3 standard deviations away from the mean, if you look at both the left and the right tail, there's only about a 0.15% out there, or 1.5% out there. So there's not much there. So over here, there's half of that. So there's really nothing here. This is extremely unlikely to happen. And so you might say, well, either my sampling was off and I didn't do a good job of getting a representative sample of the 1,000 largest cities in the world, which could be true. But if you trust that you did a good job and your sample represented the 1,000 largest cities in the world, you could say, well, then I trust my data, and so I'm going to conclude that this is really far away from what it was in 2007, and it is significantly different. And this is what we usually talk about as p-values. So this line here at 3.2 that I've put, 3.2 standard deviations above the mean is really far away, and so we could even calculate the likelihood of this. So for instance, we could say, well, okay, let's say how many values are there that are beyond the 3 line here. So we've only got 2 values, right? There's 2 values greater than 3. Those 2 values, if we said our cutoff was 3, let's say once it's past 3, then we know that it's significant. We could then count those values and say, well, there's 284 values that were simulated here. So we could say, well, that's only 2 out of 284 times that I'm going to get something that is at least 3 standard deviations away. Or maybe we want our cutoff to be 2.5. So we use the value 3. And so 3 out of 284. So, there's nothing there. That's going to be really small. So if we go here and we put a 3 here, we get a value of 0.01. So in other words, 1% of the time there is going to be a random sample of 100 that gives us a mean greater than 3 standard deviations away from the population mean. So that's extremely small, very unlikely to happen by chance. So because it's very unlikely to happen by chance, we could conclude, yeah, this is too unlikely to have happened by chance because I think my data actually does represent the 1,000 largest cities in the world. So I'm going to say this is significantly different than the 2007 data. And this is what a p-value is. So this p-value, this z-score here, is what we would use to calculate a p-value, and our simulated p-value is literally just this likelihood, this probability. How often does it happen that something is greater than or equal to a particular distance away from the mean? So you sort of think of that ahead of time and consider where do things become so unlikely that you don't believe it anymore that it happened by chance. So I hope that this video has been helpful for you in thinking about sampling and sampling distributions and beginning to think about p-value and keep thinking about these ideas. But sampling distribution is a difficult concept for a lot of people to grasp. So let me know how your thinking is going with this, and I hope that this video was helpful for you.